All right, so what I'm going to show you here is how light relates to the first quantum model of the atom. So everything we've been talking about with wavelength and frequency hopefully should come together right now. All right, light is a form of energy. So if I ask you, what is light? I'm looking for one word. Light is energy. Okay? And it's a form of electromagnetic radiation. And so it's similar to radio waves and microwaves and X-rays and all of that. But at the end of the day, light is energy. And the energy of light is related to the wavelength and the frequency of light. And so we have a couple of equations that relate wavelength and frequency to the energy of light. So when we're talking about frequency, that's the F right here, we have this equation, energy equals Planck's constant, which is a number that you don't need to worry about right now, times the frequency. And so what this is telling us is that if we increase the frequency of a light wave, we're going to increase the energy because we're multiplying by a bigger number here. So if I ask you, what's the equation that relates energy and frequency? You're going to write E equals HF. And the relationship is, it's a direct relationship. And so what that means is, as frequency increases, energy increases. And along the same lines, as frequency decreases, energy decreases. So a direct relationship means that both variables change in the same direction. As F goes up, E goes up, and vice versa. Now, if we look at the relationship between energy and wavelength, so this is the Greek letter lambda, and it's kind of like an upside down Y. Because wavelength here is in the denominator, if wavelength increases, then we're dividing by a bigger number. So our energy is going to decrease. This is called an inverse relationship. So as wavelength increases, energy decreases. And as wavelength decreases, energy increases. So as one variable goes up, the other goes down, and vice versa. Now, the wavelength of light is related to the frequency of light, which is related to the energy of light. Now, I would suggest you have the slides up here, because then this is all in color. But what you'll notice is that if I have, this is the visible spectrum of light. So these are all the colors we can see. So it's the colors of the rainbow. It goes from violet all the way to red. And what you can see is that violet light has short wavelength. And because it has a short wavelength, that means it has a high frequency and it has high energy. So higher frequency, shorter wavelength means higher energy. Whereas red light has a longer wavelength, and remember, a longer wavelength means a lower energy. So the wavelength corresponds to the color of light that your eyes can detect, and that corresponds to the energy. And this is going to be really important when we're talking about atomic theory. So again, I would suggest you look at the slides, this slide, because this is much more apparent in color. So a really important experiment was done where hydrogen gas was isolated in a gas tube that looked like this. And what they did is they put an electrical current through this. And the electrical current is a form of energy. So when they passed energy through this isolated hydrogen gas, the gas emitted light, so it lit up, just like this. So once again, when energy, electricity, was passed through an isolated gas, the gas emitted light. It lights up. And this is the really important part. When they put the light through a prism to break up the light waves, distinct lines became visible. So right here, we're looking at the hydrogen spectrum. Again, if you look at the slide, it's in color and it's way easier to see, but you see 3 distinct color bands. And remember, the colors correspond to wavelengths, which correspond to energies. So you're seeing distinct energy levels for the atom. And then in this case, this is a hydrogen atom. So what these distinct colors mean is that the hydrogen atom has distinct energy levels. And we're going to talk about what this looks like and why it's important. So what scientists proposed was happening is that there's like a ground state, a lowest energy state for the atom. And when we add energy, that excites the atom. It puts it up to a higher energy level. We call this an excited state. And when the atom relaxes back down to the ground state, that extra energy has to go somewhere. And it's emitted in the form of light. Now, what distinct colors mean distinct energy levels? Distinct means very specific energy levels. So we always see the same colors because there are very specific energy levels that the atom can go to. So this is just another way to represent it. So if we start in the ground state, and again, if you go to the slides, I animate this. This is the lowest energy state. So we start in the ground state, and if we add energy, that bumps us up to a higher energy level, which we call the excited state. When the atom relaxes from the excited state and finally goes back to the ground state, this extra energy has to go somewhere. And what happens is it's emitted as light. Now, this idea was really important because it led to the first quantum model of the atom. So there was a scientist named Niels Bohr, and what he proposed is that he was working specifically with the hydrogen atom, which is the simplest atom, 1 proton and 1 electron. And so he proposed that the electron of the hydrogen atom is moving around the nucleus in these circular orbits. And this might be a picture that you're familiar with that you've seen in the past. And he proposed that each orbit is at a different energy level. So closest to the nucleus is the lowest energy level, and as we move further from the nucleus, we're getting to higher and higher energy levels. And so what he proposed is that if we add energy to this electron, which is in the ground state, the lowest energy level, that can bump this electron up to a higher orbit energy level. And when this electron has to eventually return back down to the lower energy level, it emits light. And so this change in energy corresponds to a certain wavelength of light that we can see, and that's why we always see the same wavelength in this case, or the same color, because there are distinct or specific energy levels that the electron can exist at. Along the same lines, if this electron gets bumped up to a higher energy level, it's eventually going to have to return back down to the lower energy level. But look, we have a bigger difference in energy, so we have a different wavelength of light that would be emitted. That's why we can see multiple colors, because the change in energy here is different than here. And the change in energy is going to correspond to a different wavelength, which is going to correspond to a different color. Again, I animated all of this in the slides, and I would suggest you take a look at that. That's what all this is here. But to summarize, Bohr proposed that electrons exist at distinct energy levels, and this is where the quantum term comes in. Distinct energy levels are quanta. Okay? This is really important, and this is going to be kind of the punchline for the rest of what we're going to talk about the next week or so. So when energy is added to an atom, the electrons move from the ground state energy level to the excited state. When the electron returns to the ground state, that extra energy gets released as light. And the different colors are due to the different changes in energy levels, so that corresponds to different wavelengths that we see as those colors.